Hello friends, and welcome to another sleepy science journey. Tonight, we drift through something we chase every day, but never truly touch time itself. The clocks hum, the stars wheel above us, and still, the hours slip like sand through steady hands. But what if they didn't? What if a person could walk into tomorrow and return before breakfast? What if seconds stretched like silk, slowing your heartbeat while years raced by elsewhere? Can a man, through speed alone, live longer than his twin? Could the future already exist, waiting quietly for us to arrive? It sounds like fantasy, but physics whispers that it's not. Hidden in equations, in satellites circling overhead, and in particles born high above the clouds, time already bends. Because if time can bend, maybe the future isn't a distant land at all. Maybe it's a shadow already cast, and we're just catching up to it. Airplanes, satellites, even tiny particles in the upper sky, they've already taken brief steps ahead of us, proving that travel through time isn't a fantasy, just a difference in pace. Each of us is already moving through time's current, some a little faster, some a little slow. So tonight, we follow that current to see how far it can truly take us. We won't chase portals. We'll listen to clocks. It isn't a promise, it's a measurement. Time travel into the future arrives as fewer counted seconds on a moving clock. A moving clock quietly gathers fewer seconds than the matching clock you keep beside your bed. That calm difference is special relativity in action, and it has been weighed with instruments steady enough to hear a fraction of a heartbeat. Atomic clocks flown on long routes eastward and westward come home with small, predicted offsets, once speed, direction, and Earth's rotation are folded into the reckoning. Comparable clocks aboard satellites drift in a way that is no surprise to engineers. Altitude and motion both shape the pace of time, and the shape is written into their designs before launch. The rule is steady. As relative speed grows, the factor that stretches time strengthens. At walking pace, the change is microscopic, but it never falls to zero. Particles produced high in the atmosphere offer a crisp demonstration. Unstable muons, born from cosmic ray collisions, should vanish long before they could reach detectors near sea level if their lifetimes were the same everywhere. They do reach us, in large numbers, because their internal clocks slow while they race close to light speed. Laboratories rely on that slowing when predicting lifetimes inside accelerators, and measurements follow the forecast without fuss. People feel none of this directly. A pilot cannot sense nanoseconds slipping off a red-eye crossing. An astronaut cannot notice microseconds skimmed from a month in orbit. Still, the accounts do not add to the same total when compared with a ground reference. Speed tends to slow a traveler's ticking, while the weaker gravity at orbital height nudges it the other way, very slightly faster. Mission planners compute both contributions together and correct the onboard systems accordingly. The astronauts themselves carry the result in the tally of their days, not as a sensation, but as an honest count that differs by a breath. Nothing about the effect invites paradox or threatens cause and effect. Each traveler follows a path through space-time and counts proper time along that path. Two routes that separate and later rejoin can be compared without ambiguity, because the geometry decides what each clock has gathered. The metric defining space-time assigns intervals to events the way a map assigns distances to towns. A winding route accumulates a different interval than a straighter one, and the difference is no bookkeeping trick. It belongs to the path itself. Push the speed high enough, and the difference becomes dramatic. If a crew could accelerate to a large fraction of light speed, cruise for a while, and decelerate to return, their onboard time would lag far behind the calendars kept at home. Months for the crew could correspond to years for friends waiting on Earth, computed by the same compact relation that guided modest experiments. no shimmering portal is required. The difficulties belong to propulsion, shielding, and life support, not to the logic of time. Within the allowed lanes, future skipping is simply the rhythm of motion. Satellites already live by these rules. Global navigation systems rest on constellations of transmitters whose raw clock rates do not match ground standards by default. Because the satellites move swiftly and circle far above Earth's surface, their frequencies would drift without compensation. Control centers pre-bias the rates and upload corrections so that receivers on the ground interpret signals without wandering down the wrong street. Maps remain trustworthy because relativity is treated as an everyday utility, not a curiosity. Wider networks feel the same boundaries. Synchronizing data streams across oceans requires care with light-speed delays, platform motion, and the turning Earth beneath the cables. Financial exchanges stamp time with disciplined precision. Radio telescopes separated by continents align their recordings to the fraction of a wave so that distant objects can be imaged as if by a single dish the size of the world. Metrology labs compare their standards through fiber links and satellites while modeling the planet's shape and gravity field to remove subtle biases. These quiet habits keep distributed systems coherent, and every habit acknowledges the same restraint. Time is local, but it can be reconciled. The relation at the center is compact. The time accumulated by a moving observer equals the stationary observer's time, multiplied by a factor determined by relative speed. As speed approaches light's pace, the factor grows, and the moving clock advances more slowly. Nothing outruns light locally, yet approaching its limit suffices to produce meaningful dilation. Designers studied trajectories that deliver high fractions of light speed for probes that might someday travel between stars, not to conjure fantasy, but because the numbers do what the equations say they must. Airborne experiments confirmed the ideas decades ago by carrying matched clocks around the planet in opposite directions and comparing them with a reference on the ground. Differences in sign and size aligned with calculation once planetary rotation and aircraft speeds were included. More recent campaigns used transportable optical clocks with still finer stability. They show that careful modeling of motion, height, temperature, and stray fields brings theory and readout together with a quiet handshake. Across domains, the pattern repeats. Sharpen the instruments, keep the models honest, and relativity remains a companion, not an adversary. On the human scale, the totals remain small. A scientist living for years on a high plateau will age a touch faster than a twin at sea level because gravity is weaker there, while a frequent flyer will age a touch more slowly than a neighbor who rarely moves at speed. The differences gather as thin slivers over long periods. They matter to instruments before they matter to birthdays. That perspective helps the feeling settle. Dilation is real and measurable, yet gentle in ordinary life. Stories sometimes imagine escaping consequences by outrunning time. Physics offers kinder boundaries. Every observer carries a personal rhythm tied to their path. Signals remain capped by light speed, so messages cannot leap ahead to rewrite causes. A traveler who returns younger than a friend has not slipped the knot of history. They have simply taken a route that held fewer ticks between the same two meetings. Calendars diverge, but memories line up in a consistent order because information never steps outside its light-drawn cones. Instruments do not need rest to keep these truths. An atomic transition repeats with dependable regularity inside a careful vacuum. A microwave resonance holds steady within a chilled cavity. Laboratories nurture these references and compare them across the globe, and the comparisons read like a patient conversation among clocks. They agree that motion and gravity shape the measure, and they agree on how much. That coherence supports weather forecasting, satellite orbits, secure communication, and the location dot that appears when you ask your phone for the way home. Consider what this means for travel dreams. A generation ship, drifting slowly, would keep near parity with home. A fast courier built by a future industry could cross distances that seem forbiddingly large on a human timescale while its crew experiences a shorter span. Planning such missions would require careful accounting of acceleration, coasting, and braking to balance propellant against time gained. Protecting biology, maintaining habitats, and shielding against interstellar dust would dominate engineering concerns. The calendar difference would arrive as a natural dividend of speed. If a single image helps, picture an oval track with honest lanes. The runner nearer the center needs fewer steps to touch the same tape. The race is fair because the geometry is clear. In space-time, the lanes are world lines, and the steps are seconds. Different routes between the same two meetings yield different totals, and every careful observer can compute them. The metaphor can rest quietly because the facts already hum. Motion tilts the schedule. Position nudges the rate. Clocks record the story faithfully. The feeling that follows is modest confidence. Knowing that motion can soften one's passage through time encourages patience with the different paces we carry. It reminds us that comparison is always tied to a frame and that fairness lives in clear definitions. The universe grants each traveler a quiet metronome that does not lie about their path. When friends reunite after long separations, the difference recorded by machines is small but real. It is a souvenir of motion, not a crack in affection. As the weight of the world gathers, a second loosens its stride. General relativity says why with a quiet certainty. The rate of time depends on gravitational potential, and deeper positions in a field count fewer moments than higher ones. The statement is not a flourish. It became evidence when physicists sent light up a building and saw its color shift, a small step toward longer wavelength that matched prediction. It became routine when laboratory clocks, stable to many digits, showed a detectable change after being raised by a modest height. The principle is simple to say and careful to use. Where gravity presses more strongly, local processes run a little slower relative to distant standards. Where the press eases, they quicken by the same clean rule. A tower experiment in the middle of the last century provided an early sturdy signpost. Gamma rays sent upward through a few dozen meters, arrived, slightly softened, and the measured change landed on the value calculation foretold. That result linked time and gravity in a way that no longer required grand cosmic scenes. Later, better clocks narrowed the test. Teams compared identical devices on different floors and watched their ticks drift at the gentle pace expected from the change in height. The effect is tiny over rooms and corridors, yet it meets the math faithfully. Raise an optical clock by a human step, and the signal changes in the 6th or 7th decimal place. Lower it again, and the difference unwinds. Nothing mystical moves. The geometry guides the count. Close to compact masses, the same logic grows firm and visible. A neutron star compresses more than a sun's worth of matter into a city-sized sphere. Near its surface, time measured locally lags sharply behind the rhythm marked in distant space. Spectral lines from materials circling such an object arrive shifted, not only by motion, but by the climb out of strong gravity. Models that fit those lines must include both contributions and observations, reward the inclusion with agreement. In binary systems where a dense remnant tugs a companion, timing data reveal relativistic corrections that are inseparable from gravitational time dilation itself. The clock that sits near such a mass obeys the local shape of space-time, and anyone far away who reads its output must translate. A black hole steepens the landscape further, Coordinates chosen by a far observer describe processes near the event horizon as ever slower, while a traveler falling inward records an ordinary span to the boundary. This is not a contradiction. It reflects two different vantage points, each using its own proper clocks and rulers. Light trying to escape loses energy, its frequency sagging as if breath were drawn from a long climb. That change is one face of the same geometric feature that slows the local second. Emission from hot gas just outside a non-rotating hole's innermost stable orbit carries these marks in every photon. The practical consequence is a map of brightness and color that tells us about gravity's shape near the edge. Observatories that read X-ray flicker from such regions build the curvature into their interpretation as a matter of course. On Earth, the gentler version of this rule underpins navigation and timing. A satellite's onboard oscillator does not keep pace with a ground reference by default because its altitude lifts it to a higher potential, even as its motion changes its rate in the opposite sense. Control centers fold the gravitational term into the models that steer each craft's time solution. Receivers on the ground also compute their position using a reference surface tied to Earth's gravity field, not an ideal sphere, so that elevations and regional variations are handled honestly. The corrections are part of the plumbing. If omitted, position errors would grow quickly and maps would wander. Because they are applied, ordinary devices reconcile their answers with quiet precision. Metrology treats the same phenomenon as a tool. National laboratories compare primary standards across countries and seas. When they line their digits up, they do not ignore height. Transfer links include models of Earth's potential so that each lab's local seconds, shaped by its altitude, are put on equal footing. The care is worth it. As optical references improve, the sensitivity to height improves with them, turning clocks into sensors of gravity that can, in principle, chart changes in groundwater or crustal motion. By recording tiny shifts in tick rate over time, timekeeping becomes surveying. A field once content with counting vibrations now listens for the rise and fall of the planet itself. Astronomers meet gravitational time dilation whenever light climbs or descends by large amounts of potential. The redshift from dense stars changes the shape of spectral features. The delay that a signal suffers passing near a mass follows a related path. Timing of pulsars, which are rotating neutron stars radiating with extraordinary regularity, depends on folding these effects into every arrival. When two of them orbit tightly, or when one orbits a black hole, the combined influence of motion and gravity stamps each received pulse. Analysts who fit the sequence must account for the slowed seconds near the deeper well and the stretched trajectories crossing curved space. With that accounting, the fits hold steady year after year. The practical lesson generalizes beyond observatories. Any comparison of separated clocks needs a story about potential. A fiber link, spanning mountains and valleys, carries more than bits. It carries assumptions about the heights of the endpoints. A portable reference moved from a basement laboratory to a roof will not agree with itself until the difference in gravitational potential is written into the final line. Engineers manage this by adopting a conventional timescale to which all local readings are related. Each device lives honestly inside its neighborhood, and translation does the rest. It helps to picture a relief map where closer contour lines mean a steeper slope. Gravity is the spacing, and time is the hiker's pace that follows. In a deep valley, the steps shorten, not because the walker is unwilling, but because the ground requires it. Up on a ridge, the stride lengthens by the same quiet rule. The path remains continuous. The walker remains the same person. Only the terrain has changed the count. Near rotating compact objects, additional structure appears. Frame dragging twists space in the vicinity. altering the orbits that are possible and the way time accumulates along them. In that environment, calculations use metrics that include both the gravitational potential and the rotational terms, and both enter timing models for emission from the inner regions of accretion flows. Although the topic belongs more to dynamics than to clocks on desks, the moral is consistent. Gravity in all its forms shapes the schedule of processes, and a careful observer always asks which reference defines the word second before comparing two counts. Human feelings live easily inside this picture, waiting at sea level for a message from a friend working high in an observatory. You are both inhabiting seconds that are locally faithful and globally unequal by the smallest margin. You do not notice the difference, yet instruments do, and they reconcile it every time your devices exchange signals. The thought invites a kind affection for clocks. They are not tyrants. They are neighbors agreeing on how to translate each other's accents. It is tempting to ask whether one could exploit gravity's influence to push farther into the future by sitting beneath a dense mass. The physics answers politely, but firmly. Achieving a noticeable change requires potentials that accompany environments hostile to fragile bodies. The gains increase as the risks do. Earth's modest field provides measurable differences for instruments and negligible dividends for personal calendars. The schemes that push the effect toward dramatic values move the discussion from comfort to survival, and survival becomes the only subject that matters. Even so, the gentle case remains a gift. Because gravity slows a second in known ways, we can navigate oceans with satellites that would otherwise fall out of step. We can frame international timescales that let telescopes work as one ear. We can improve maps of the planet's own mass by listening to clocks rather than only weighing mountains. Every application depends on the same quiet statement. Local time is shaped by place, and place is defined by gravity's curve. If a soft comparison helps the idea settle, imagine pressing a fingertip against a pane of glass and feeling the material push back. The glass curves slightly under the pressure, and anything that tries to move along its surface adjusts to the change without complaint. Gravity's presence curves the stage on which processes run, and those processes accept the new tempo as part of their setting. Chemistry, biology, electronics, all of them keep their private rhythms, but the translation to a faraway reference will show a clean, small shift set by the surroundings. Across decades of tests, the story has not wavered. From towers and rooftops to mountain labs and satellites, instruments repeat the same agreement with the theory that binds space and time. That steadiness nurtures trust. It lets agencies plan missions and researchers publish predictions, knowing that the correction for height is not a negotiable opinion. It is the discount or premium gravity charges when you choose a flaw. To speak of "at the same time" is to choose a frame before choosing words. In special relativity, two distant events that share a timestamp for one steady observer can separate in order for another who glides by. The change is not a trick of clocks behaving badly. It flows from the rule that information travels at light speed, and that each observer builds coordinates using that constant. Synchronizing distant clocks in one frame means light pulses are sent, reflections are noted, and midpoints are defined by equal travel times. Shift to a frame sliding past, and the symmetry of those pulses tilts. The same flashes reach one station sooner and the other later. A book that was aligned along one spine becomes skewed along another, and the page numbers no longer match across the width. Rail platforms and passing carriages provide a plain demonstration in thought. Two lamps at the ends of a long carriage fire together in the carriage's own rest. A traveler seated halfway sees the flashes arrive as one. A person on the platform, watching the carriage roll forward, sees the front flash meet a point moving toward it, and the rear flash chase a point moving away. Because light's speed is the same for both flashes, the front one arrives sooner in the platform frame. That observer judges the front lamp to have fired earlier. Neither person is wrong. Each has used a procedure faithful to their motion to define simultaneity, and the definitions differ. This tilt of now slices space-time into different layers for different motions. Diagrams draw it cleanly. World lines trace histories, and planes of simultaneity slice across at angles that depend on velocity. No single cosmic present lines up for everyone. The consequence is calm, not chaotic. Cause still precedes effect, because light's cones fence off what can influence what. Two events, outside each other's cones, cannot be made to switch cause and effect by any change of steady motion. They can, however, swap before and after labels between observers without harm to the order of influences. That is why experiments agree across frames once data are transformed properly, and why broadcasts, trades, and measurements can be reconciled without a master clock in the sky. Practical systems live inside this geometry. Distributed computing compares timestamps across moving platforms and rotating Earth, and then reorders transactions with conventions that define a common scale. Time servers apply corrections that account for signal propagation, equipment delay, and the motion of both sender and receiver. High-energy laboratories reconstruct collisions by transforming detected tracks back to the rest frame of a short-lived particle. Because lifetimes and angles measured there explain yields measured here, astronomy arranges observations from observatories in different latitudes by converting each record to a standard coordinate time tied to Earth's orbit and rotation, so that a flare seen on one ridge can be matched cleanly to a burst seen on another beach. Each example leans on Lorentz transformations, which link one steady frame to another with relations that preserve light speed. Those relations also explain time dilation and length contraction as two faces of the same mapping. A moving clock accumulates fewer ticks between meetings, and a moving rod aligns shorter along the direction of motion, as seen by a stationary observer. The relativity of simultaneity completes that trio. It is the reason the shortened rod and the slowed clock fit together in a consistent picture. Remove the tilt of now, and the other effects would contradict each other. Keep it, and the trio interlocks. Thought experiments about twins parting and reuniting derive their clarity from these same ideas. One twin stays home, the other departs at steady speed, turns, and returns. Each segment of motion can be analyzed from appropriate frames, and the world line of the traveling twin includes accelerations at departure, reversal, and arrival. When proper times along both paths are integrated, the traveling twin's span is smaller. The result is not a paradox, but a comparison of different curves between the same events. The symmetry is broken by the accelerations that mark the traveler's change of frame, and the calculation matches what careful clocks would show. Aviation tests have carried clocks on loops to resemble the twins' departure and return in miniature. The sums line up with the theory when all motions are included. Relativity of simultaneity also touches how we think of memory and coordination. Inside a spacecraft coasting steadily, crew members can define a shared present and operate as if the rest of the universe were sliding by. Outside, mission control defines its own present. Bridging the two requires agreed procedures to convert coordinates and times. Signals are packaged with information about transmission and reception, and flight dynamics models translate between the two rhythms. Navigation from deep space, therefore, includes light-time corrections and relativistic adjustments that fold in both dilation and simultaneity shifts. The discipline pays off in predictable arrivals and honest images returned from planetary flybys. Networks on Earth do something similar on smaller scales. Fiber links carry time signals between standards labs, and every chirp of timing includes knowledge of how long it took to travel, and through which media. The receiving end subtracts path delays and reconstructs the sender's intended reading. Satellite time transfer does the same with added layers for orbital motion and atmospheric delay. Distributed ledgers and exchanges add further conventions for ordering, because earlier and later across distance cannot be assigned without a model. Engineers do not lament that absence. They treat it as a design constraint, like bandwidth or noise. Relativity's view of simultaneity sometimes invites a block-like picture of space-time. Events laid out in a four-dimensional quilt, where paths weave and never tear. One need not commit to a philosophy to work with the physics. It is enough to notice that the absence of a single plane of now removes the pressure to locate a privileged instant. Schedules become local stories, linked by light. Predictions become agreements among frames, rather than edicts from a master timekeeper. The cosmos stays coherent, because influences stay within cones, and because transformations convert one account to another without ambiguity. Communication protocols embed these practices. Space agencies print documents that specify frame definitions for all tracking and commanding. Scientists who combine radio telescopes into a globe-sized ear define a conventional time that all stations aspire to follow, and then they transform data into a barycentric frame that peels away Earth's spin and orbit. Observatories that witness transient events fold light time from the source into their analyses, acknowledging that what they call the same instant is a practical, agreed slice rather than a universal sheet. In every case, the work proceeds because the recipes are repeatable, not because time has been tamed into a single drumbeat. Education sometimes offers a picture to settle the mind. Two photographers on different hills capturing the same lightning strike. The frames do not align, yet the bolt is one, and a transformation maps one image to the other. The feeling that follows is steadiness. We cannot insist that distant clocks share a beat in all motions, but we can always learn how to compare beats honestly. That honesty is what makes flight dynamics stable, networks synchronized, and experiments readable across labs and seas. The human anchor arrives gently. Friends separated by distance may send messages marked "now" that do not land together. The delay is practical, and the label is local. Feelings reconcile by kindness rather than by denial. Physics places boundaries on how quickly influence travels, and how much two observers can disagree about order without harming cause. Within those boundaries, the world is generous. It allows many presents to coexist and provides translations where cooperation is needed. And when attention turns toward tunnels drawn by equations or loops whispered by rotating solutions, this tilted notion of now becomes the quiet preparation. If simultaneity is frame-bound and cause lives inside light cones, then architectures that claim to leap between distant moments must answer to both. The groundwork laid by moving lamps and sliding carriages is not toy work. It is the grammar that any advanced sentence must speak clearly before asking for extraordinary meanings. Equations that describe gravity permit shapes stranger than hills and hollows. Among them are corridors, wormholes that join separated regions, like secret halls in a house with no shared walls. The first of these, the Einstein-Rosen bridge, appears when extending the solution for a non-rotating black hole. It ties one exterior region to another across a throat. The catch is immediate. The throat pinches shut too quickly for anything to cross. A traveler falls in and meets an end that is not a door. Mathematically, the connection exists. Physically, it behaves like a vault without hinges. Later work asked whether a passage could remain open. The answer sketched a condition. The throat would need support from matter that, measured by certain observers, possesses negative effective energy density. Classical fields and ordinary substances resist that request. They obey energy conditions rules that keep densities positive and flows well-behaved. Quantum fields, however, complicate the story by allowing local, temporary dips below the vacuum's baseline in special arrangements. The Casimir setup, where two conductive plates sit very close in a vacuum, shows a force that arises from such a dip. The sign is promising. The scale is not. The region is narrow, the magnitude modest, and other theorems limit how much negative energy can be accumulated and for how long. Stability complicates the picture further. A traversable throat, if built, would need to survive radiation streaming in, particles wandering through, and the space-time's own tendency to respond to disturbances. Analyses suggest that small perturbations can grow in ways that collapse the passage or flood it with quanta drawn from the vacuum. The prospects of guiding a human-scale craft safely through such a corridor while the environment remains realistic are thin. The passage would have to be engineered with a tolerance and control beyond any known scheme. Even then, one must mind feedback loops that could turn a gentle fluctuation into a destructive surge. Observations give no hint that nature provides these corridors ready-made. If a wormhole with a macroscopic throat linked two regions in our sky, light passing near the entrance would distort differently than it does around an ordinary mass. Surveys that map lensing by galaxies and clusters see arcs and rings that fit models with conventional matter distributions. The signatures match gravity's influence by hills and valleys in the field, not by mouths and tunnels. High-energy transients, catalogued by space telescopes, also find explanations in mergers, collapse, and magnetized plasma, rather than in sudden transit of matter across a shortcut. The temptation to use a wormhole as a time device leads to a delicate construction. Suppose a traversable tunnel existed. If one mouth were accelerated to high speed and brought back, or parked in a deeper gravitational potential than the other, the two ends would accumulate different amounts of time. A traveler stepping through could emerge before or after, relative to external coordinates, depending on the arrangement. The strategy is neat on paper, yet building the premise asks for the same exotic matter and the same stability not yet found. Moreover, feedback from quantum fields near configurations that approach closed timelike curves may grow without bound, a hint from semi-classical gravity that chronology tries to protect itself. Proposals sometimes suggest patching together arrays of Casimir-like elements to produce a macroscopic negative energy region. Quantum inequalities stand in the way, limiting the product of magnitude and duration for such dips. The vacuum will not allow a simple stacking of many small effects into a large, persistent reservoir. Other ideas point to squeezed light and states engineered in cavities to manipulate energy density locally. The achievements are real in optics and sensing. The gap between those tabletop arrangements and the volumes needed to support a throat large enough for transit remains enormous. The merit of wormhole studies is not lost in these obstacles. They teach us what the field equations can describe and where additional physics must intervene to keep the world coherent. They link the geometry of gravity to the stresses that source it, reminding us that spacetime's shape is not free to wander without accounting for the material budget. They also bridge conversations with quantum information, where entanglement and correlations inspire analogies that guide intuition about connected regions. These bridges are conceptual, not literal. They clarify by resemblance rather than by offering a route for boots. If one insists on an image to hold these conclusions softly, imagine an architect's arch that calls for stones lighter than air, and stronger than diamond to remain standing. The curve is graceful, and the loads are analyzed correctly. The bill of materials returns blank lines, where the essential pieces should be. In that emptiness lies the present verdict. The theory permits, but the shop floor does not deliver. Astronomy does not see the footprints, and laboratories do not find the bricks. The absence of evidence is not proof of impossibility. It is, however, a compass for attention. The focus tilts toward energy conditions, quantum limits, and stability analysis, because those are the gates closing the passage right now. Perhaps a future theory of gravity that includes quantum structure at the smallest scales will change the conditions. Perhaps effects near singularities soften, or emergent behavior permits structures that classical reasoning forbids. Such hopes deserve curiosity but not premature certainty. Meanwhile, engineering that depends on wormholes remains fiction with a good bibliography, not a manual with parts lists. And yet, the question that drew us here retains its quiet glow. If space and time are one geometry, then connecting far regions with short lines is a natural thought. If time accumulates differently at different ends, then steps through a connection could displace a traveler in calendars as well as kilometers. Those ifs are generous, and their doors remain closed by costs that current physics calculates. The corridor stays on paper, and the hands remain on ordinary tools. From here, attention drifts toward another family of shapes, that the equations admit loops in time drawn inside certain rotating or idealized spacetimes. Their existence in solutions is real. Their hospitality to visitors is another matter. Einstein's equations draw some spacetimes where a patient traveler could follow a timelike path that closes on itself, returning to a point that shares their own past. The idea wears several costumes. Gödel described a universe filled with matter that rotates globally. In that setting, closed time-like curves thread through the geometry like paths looping around a cylinder's surface and returning to a mark. Other constructions, imagine a cylinder of dense matter spinning so rapidly and extending without end that nearby time-like lines curl back. Inside the maximal analytic extension of a rotating black hole, there appear regions where the coordinates permit time-like loop. Each version shows the same mathematical feature. The metric allows a curve that is everywhere within the local light cones and yet returns to its start. The defects are not hidden. Gödel's world is not ours. Observations show an expanding cosmos with no global rotation of the kind his solution requires. The background microwave glow maps the early universe and places limits on any overall swirl that are far smaller than his construction demands. The infinite cylinder cannot be built. Finite cylinders, even if spun with dangerous ambition, fail to produce accessible, stable loops without additional conditions that reintroduce matter behaving unlike any catalogued form. The interior of a realistic rotating black hole is unlikely to preserve the neat corridors drawn by the ideal metric. Perturbations fall in. Gravitational focusing magnifies them. Analyses of mass inflation show divergences that turn smooth regions into turbulent, destructive zones. A traveler hoping to thread that maze would meet tides and radiation that tear predictions apart. Quantum fields add another layer of resistance. Near regions where closed time-like curves would form, calculations suggest that vacuum fluctuations can amplify, driving stress energy to values that warp the geometry in ways that prevent chronology violations from maturing. This line of thought condenses into the chronology protection. Conjecture. Physical laws conspire to keep cause ahead of effect on macroscopic scales. It is not a theorem with proof. It is a banner under which many results march in step. Wherever loops threaten to appear, infinities or instabilities answer first. Models that allow loops sometimes try a different approach. They impose self-consistency conditions. A traveler who enters a loop must act in ways that were always part of history. If they try to prevent a past event that enabled their travel, improbable coincidences intervene, and only those initial choices that lead to consistent outcomes are permitted. The logic closes without contradiction, but the price is high. Freedom narrows. Initial data no longer spread into a family of futures. They squeeze into the single thread that satisfies the loop. The picture is coherent but brittle. A nudge spoils it. Quantum information has explored analogues of such behavior in circuits that mimic the logical structure of closed timelike curves. Techniques like post-selection enforce outcomes that match a target, and experiments can simulate paradox resolution in small systems. These demonstrations are about probabilities and control, not about paths through space-time. They show that rules can be written to avoid contradictions in toy models. They do not move clocks backward or forward outside the laboratory's time. Evidence from the world beyond equations remains silent about practical time loops. Astronomy's records show no persistent signatures of processes being undone. Archives across many disciplines, weather, seismology, finance, bear no repeating anomalies that would suggest systematic rewriting. The quiet is not proof that loops are forbidden. It is, however, consistent with the idea that if such curves exist inside some ideal constructions, the corridors to them are blocked by physics that refuses to be both strong and gentle at once. Strong enough to draw a loop, gentle enough to let a person through nature, rarely grants both in the same room. A glimpse of the logic appears in how influences are fenced. Light cones bound what can reach what. To fold a time-like path back into its own past requires arranging cones so that they tilt and twist in a pattern unnatural for familiar matter and fields. The arrangements that achieve this in equations rely on distributions or global properties that do not match observation. In the few cases where a local setup could, in principle, create such a twist, the same quantum backreaction story returns to roughen the corridor. The geometry resists being trained into a knot that ties cause to its effect in reverse. Human feeling finds a place here without strain. There is a tenderness in the idea that history protects itself, not by decree, but by how fields accumulate and how fluctuations grow. It suggests that memory's direction is not imposed from beyond, but written in the way action flows through matter. Desire can lean backward, yet the stage keeps the actors moving forward. It is not a punishment. It is a kindness that keeps outcomes legible. If one still wants an image that keeps faith with the facts, think of a spool of thread that someone tries to pull back through its own weave. The fabric resists at the crossing points. Tug harder, and the weave tightens. The more energy one applies to force the reversal, the more the texture answers with knots and friction. No loom is broken, and no law is shouted. The pattern simply holds. Research continues because the questions are healthy. What does quantum gravity say about the innermost regions of rotating collapse? Do semi-classical infinities stand once a full theory smooths the Planck scale grain? If they soften, do corridors open, even for dust motes, let alone people? Until better answers arrive, the safest statement is measured. Equations allow loops in special worlds. Observations show a different world. Analyses of stability and quantum effects argue that attempts to create workable loops run into amplifications that act like alarms locking the doors. The gentle relief is that our tools do not demand impossible vigilance. We need not scan skies for backward messengers to keep calendars safe. We look, as always, for consistent explanations of phenomena, and we find them without invoking trips through yesterday. The guidance from experiments remains steady. Causality holds in the regimes we can probe, and deviations, if they exist, hide where instruments cannot yet reach. Until then, the future remains ahead in the useful sense, and the past remains a record, not a destination. In gravity's language, matter writes curves, and geometry reads them calmly. The stress-energy tensor fills that script, and the field equations answer without sentiment. Everyday materials keep a simple courtesy. Energy density appears positive to every honest observer, and flows refuse to outrun light. Physicists gather these courtesies under energy conditions. The weak and dominant versions safeguard positivity and subluminal transport. The null condition anchors behavior along light-like directions. The strong form guides how families of nearby geodesics converge when pressure and tension join density in the accounting. These conditions are not distant decorations. They appear inside the theorems that keep spacetimes orderly, singularities where collapse is inevitable, horizons with one-way character, and causal structures that do not tangle. Where laboratories peer, classical matter has honored these rules. Shortcuts ask for ruder manners. A traversable tunnel between distant locations must not pinch closed, yet gravity urges collapse. To counter that urge inside the throat, effective energy density must be negative for some observers. A space-time bubble that lets a cabin drift while space moves would demand rings of stress that bend geometry the other way. The equations allow such shapes if the ledger contains entries with the required sign and size. The difficulty is not algebra, it is inventory. Ordinary fields do not sit in macroscopic, long-lived configurations with negative energy density. The very theorems that protect global behavior lean on that absence. Quantum fields complicate the boundary by permitting brief, local dips below the vacuum's baseline. In special preparations, the expectation value of energy density becomes negative for an instant and a small region. The classic Casimir arrangement, two clean, close plates in a vacuum, pulls inward with a measurable force that implies such a dip between them. The sign is promising, but the account closes quickly. Quantum inequalities limit how negative the energy can be and how long it may stay that way, with bounds that tighten as regions grow or durations stretch. Attempts to tile space with many small deficits do not evade the totals. The inequalities stand like walls around the storehouse. Sketches of warp-like metrics bring the bill into view. Early estimates for a comfortable bubble asked for negative energy, comparable to astronomical bodies, arranged with exquisite precision around a thin rim. Later refinements adjusted profiles and reduced totals by orders of magnitude, but the shopping list remained exotic. Intense negative bands beside compensating positive shells, all tuned to keep the global budget consistent. Even in friendly versions, tolerances read like a jeweler's specification for a hummingbird's pulse, delicate, unforgiving, and vulnerable to drafts. The coordinate advantage inside the cabin does not reduce the cost outside. The geometry still demands a source with unfamiliar sign and shape. Astrophysics shows torrents of energy and pressure, but almost always with the familiar sign. Accretion flows blaze in positive quanta. Relativistic jets carry kinetic power across thousands of light years. Magnetic fields hoard and release energy in flares. These are bright storms, not cool wells. Surveys of gravitational lensing around galaxies and clusters reveal arcs and rings consistent with ordinary mass distributions. No mouth-like distortions demand negative reservoirs. The sky spends lavishly, yet nothing in its accounts resembles a persistent, steerable stock of negative energy that could be tapped and shaped into a transit structure. Laboratory platforms confirm the promise and the wall. Casimir forces are real and measured with delicate balances and micro-resonators. Squeezed states in optics redistribute quantum noise. creating moments when certain observables dip beneath classical limits. These tools sharpen sensors but do not fill rooms. The negative portions live in tiny gaps or fleeting intervals, surrounded by compensating positives that preserve global accounting. Metamaterials bend electromagnetic waves and mimic refractive tricks, yet they manipulate fields in media rather than space-time itself. Cloaks for light are not corridors for travelers. Engineering, if it ever enters the story, must answer dull questions that ruin fanciful margins. Where will the fields come from, and how will they be fed? What structures confine them, and how do supports handle heat, radiation, and mechanical stress? Losses in conductors and dielectrics become ordinary demands on power supplies. Any leakage from a negative region into standard modes erodes the very stock one hopes to use. A practical design would require sources, confinement, and cooling operating at tolerances that leave little room for noise. Thermal motion, cosmic rays, and imperfections in materials would nudge the rim and the throat. Each nudge would shift stresses, and the feedback would not be gentle. Back reaction makes the hallway tighter. Fields sculpt geometry, and the changing geometry sculpts the fields in return. A ripple of radiation, a drift in boundary conditions, and the balance shifts. In configurations flirting with closed timelike behavior, semi-classical estimates often find stress energy blowing up as quantum fluctuations amplify. The more sharply one draws the rim, the more intense the response becomes, as though the vacuum raises its voice exactly where chronology would blur. Smooth the gradients to quiet the response, and the requirements spread over larger volumes, increasing totals and complicating confinement. The design lives between grindstones that refuse to part. Some researchers step sideways into analog worlds. Flowing fluids, cold atoms, and tailored lattices can create effective horizons for sound or light. These analogs illuminate Hawking-like emission and field behavior in curved backgrounds. They teach lessons about kinematics, not passage. A wave packet may feel an imitation of gravity, a person will not. The distinction keeps romance honest, without dimming curiosity. A calm summary runs like this. General relativity permits many geometries, yet ties them to sources with equations that care about signs. Energy conditions are the customs officers. Quantum theory stamps a temporary visa for small negative excursions, then revokes it before anyone can build a warehouse. Stability checks ask whether your cargo rattles the frame apart once you roll, and most loads that would bend time for travelers fail inspection at that door. Astrophysical catalogs show no alternative stockrooms where negative energy is warehoused ready for delivery. The absence is not proof of impossibility, but it is a map of present limits. If an image helps, picture a shipwright asked to craft a vessel that sails on a lake of negative water. The hull is elegant, and the hydrodynamics consistent if the lake exists. Every harbor offers ordinary water. Every pump delivers the same. Designers can refine joints and polish brass for years, but the day of launch never arrives because the lake remains a drawing. Wonder need not fade. It simply learns where the shoreline lies. This perspective does not forbid dreams. It organizes them. Dilation into the future belongs to engineering, faster motion, higher clocks, deeper models, clearer comparisons. Passages and bubbles belong to new physics, different sources, altered conditions, softened inequalities. Until a theory supplies materials that real shops can order, the price of passage stays beyond reach, a ledger of deficits and tolerances that present practice cannot pay. There is also the distinction between pointwise and averaged promises. Classical matter usually satisfies the null and weak conditions at every point. Quantum fields, by contrast, can dip below zero locally, but tend to satisfy averaged versions along complete light-like or timelike paths over sufficient lengths. Those averaged guarantees still restrict ambitions. A designer cannot place a long ribbon of negative energy along a route. The integral along that route will be bounded by the same inequalities that guard stability. Attempts to push around the limits usually shift burden to fewer, sharper regions, where back reaction grows louder. In that contest, chronology often protects itself without edict. The fabric answers with constraints, and proposals return to the drafting table, gentler for the lesson. Reliable knowledge grows where measurements repeat and strangers agree. Time and gravity have been tested in many rooms, by many hands, with instruments that do not share biases. Optical clocks once filled cabinets. Now they rest on tables and still resolve differences that turn a single step into a measurable change. Lift one by the height of a stair, and its rate shifts by the predicted few parts in a quintillion. Lower it, and the shift unwinds. Laboratories link these clocks with fiber cables that measure delays and preserve phase, and the comparisons land exactly where general relativity says they should. What sounds like poetry seconds stretched by height shows up as digits moving steadily on quiet screens. Flights add a steady chorus. Transportable clocks ride long routes and return with offsets matched by calculations that include aircraft speed, direction, and the rotation of Earth beneath the path. The signs and sizes follow the formulas tested for decades. Satellites continue the exercise constantly. Their oscillators would drift relative to ground standards without corrections for altitude and motion, so control segments, pre-bias frequencies, and adjust them in service. Receivers treat the satellites as beacons that sing precise times and positions. If the relativistic terms are dropped in a simulation, maps wander within hours. With them, doorways appear where they should. The same equations that teach students also guide logistics, agriculture, finance, and rescue. Particles speak with a different accent, yet echo the same line. Cosmic rays crash into air, and seed showers that include muons, unstable cousins of electrons. At rest, a muon's life is too short to fall far. At high speed, its internal time stretches, and many reach detectors at the surface. Counters buried beneath rock still log their arrivals in rates, explained by the same dilation. Accelerators repeat the lesson under control, producing beams with known energies and watching lifetimes agree with Lorentz predictions. No drama is needed. Statistics alone trace the slope, and the slope matches the rule. Strong field tests arrive from space. Binary pulsars pairs, where one member is a dense, rotating neutron star, offer clocks that keep time with astonishing steadiness. As they orbit, pulses arrive early and late by tens of microseconds that encode motion, curvature, and redshift. Long series reveal precession, gravitational time dilation within the orbit, and loss of energy to ripples in space-time. The curves fit the equations of general relativity when all terms are included. Leave a term out, and residuals grow in patterns that scold the omission. Repeat the measurement with other pairs, and the same scolding appears unless the full theory is used. Agreement across systems becomes its own. Quiet music. Imagery of extreme gravity rounds out the gallery. Interferometric arrays spread across continents resolve dark centers rimmed by lopsided rings in nearby galaxies. The ring size and brightness pattern match models where photons orbit near a deep well and then escape. X-ray light from gas spiraling around compact objects flickers with periods explained by orbits close to the last stable path. The energy shifts in those spectra require both Doppler motion and the climb out of curvature. Observations from different bands and instruments cross-check one another. When the models include relativistic redshift and time dilation near strong fields, The fit tightens. Without them, it loosens. The sky, indifferent to our hopes, keeps writing the same answer. On Earth, lasers trace rotation with care. A beam races around a closed loop in opposite directions. Supple electronics count the difference in travel time and return a rotation rate fine enough to hear the planet's daily turn. Atom interferometers split and recombine matter waves, turning phase differences into a reading of acceleration and gravity. Drop towers allow long, quiet falls that test whether different materials accelerate alike. So far, they do within stringent limits, preserving the equivalence of inertial and gravitational mass where we can check. Each device is simple in principle and meticulous in practice. Together, they weave a net that leaves little room for surprises large enough to overturn cause. Across this wide weave, one feature remains absent. No experiment records a durable sign of pastward influence. No device closes a loop through space-time and returns a message that left later than it arrived. Quantum information labs can simulate the logic of closed-curve behavior using post-selection and special circuits. Those exercises teach consistency rules and sharpen thinking about paradox, but they do not move calendars. In every physical channel we can monitor, influences remain, fenced by light cones, and sequences stay ordered. Where people hope for an exception, instruments report continuity. The strength of this knowledge is cumulative, not singular. A single test can be fooled by a hidden draft. A web of unlike tests, built in different media and scales, tends to pull errors in different directions. When answers cluster, confidence grows. The cluster says that speed slows proper time, gravity stretches it, and sequences stay within limits set by light. Inside that rule, futureward travel by dilation is ordinary yet modest. Leaps grand enough to change lives call for velocities or potentials far beyond our tools, and pastward travel finds no foothold. Navigation networks remain a daily demonstration. Receivers draw on multiple satellites, each carrying timestamps tied to a common scale. The solution for position includes a correction to the user's clock. In effect, handheld devices are brought into chorus with the constellation and with ground standards. The chorus depends on relativity throughout, in the orbital models, in the transformations between frames, and in the handling of delays through air and hardware. Engineers include these terms because leaving them out breaks the answer. The proof appears in streets that match their labels and in signals that meet where people agreed. Astronomy's housekeeping performs a similar translation. Observatories record photon arrivals and convert those logs to a standardized coordinate time located at the solar system's center of mass. The conversion peels away Earth's spin and orbit and includes relativistic pieces. Only after that step can records from mountains far apart be combined into a single, honest timeline. The sky does not supply a universal present. Observers construct a practical one with light and math, then share it with care. Slow, patient comparisons look for drift in constants. Optical lattice clocks watch ratios of atomic transitions over years. So far, within narrow bounds, the constants stay steady. That steadiness comforts designers who build on them. It says the stage has not changed beneath the dancers. Where variation might hide, instruments probe, and the answers are quiet. Whenever a claim suggests a path backward, experimentalists ask what unmistakable traces would appear if it were used. Messages sent upstream should leave statistical scars in archives. Objects looping through time should challenge inventories and conservation. Long records in many fields show no such persistent anomalies. Fluctuations behave like fluctuations. Trends reflect local causes. The absence does not end curiosity, but it sets a standard for future claims. The feeling that follows is a gentle steadiness rather than a closed door. There is wonder in clocks that can hear a stare, in beams whose lives stretch because they hurry, and in arrays that listen to heavy objects bend space-time as they swirl. The line these experiments hold is not a wall against imagination. It is a coastline where imagination launches boats and returns with maps. The boats that come back carry the same story. Dilation exists and is small at human speeds and heights. Strong fields sculpt time near compact objects. Cause stays ahead of effect in the regions we can reach. Paradoxes arrive like signposts at the edges of our rules. They do not overturn the rules. They ask whether the rules have been read carefully enough. The familiar tangle about preventing a grandparents' meeting is a clean example. If a path into the past were physically available, the question becomes how cause and effect fit inside the same loop. One approach imposes self-consistency. In that view, any action taken by a traveler is already woven into the earlier scene. Attempts to block a meeting misfire for ordinary reasons, not because fate intervenes, but because only histories that fit the equations occur. The logic closes without contradiction, though it removes the freedom to set arbitrary starting moves. Freedom narrows to what the geometry will allow along a looped path. A second approach accepts branching. Interventions in the past do not revise the traveler's original record. They seed a separate outcome line that shares a prior segment and then departs. Quantum theory accommodates superpositions and branching in some interpretations. Extending that comfort to macroscopic travel is another task. Decoherence binds large systems to classical behavior quickly, and maintaining delicate quantum control across a person-sized vehicle is far from present methods. Branching remains a language about possible structures, not a tool that repairs old events in one continuous ledger. Information puzzles tighten the knot. The bootstrap example imagines a design, a tune, or a message with no origin circulating along a loop forever. Physical models that permit such cycles require fine alignment of conditions. Small disturbances, thermal noise, or environmental couplings tend to disrupt the loop and smear the content. The practical lesson is modest and precise. If a model depends on perfect repetition to work, the first unmodeled nudge will spoil the trick. Stability under perturbation becomes a test as important as bare logical consistency. Systems that fall apart under small noise are not realized in a world filled with vibrations and imperfect insulation. Predestination motifs in stories highlight feedback. An attempt to avoid an outcome becomes part of the chain that creates it. The pattern mirrors control loops in engineering. A system with delays and gains can overshoot in ways that feed the very behavior being corrected. The appearance of inevitability follows from dynamics under constraints, not from metaphysics. With time in the loop, the analysis inherits the same lessons. If a proposal for pastward travel generates unstable responses for small deviations, its behavior will be dominated by that instability long before any romantic aim is reached. Physics answers paradoxes with local structure. Influences propagate within light cones. Energy and momentum are conserved within interactions. Fields couple in ways encoded by symmetries that experiments have measured. Models that propose closed, timelike behavior must sit inside that scaffolding and still satisfy it when the details are spelled out. Many do not. When calculations include how quantum fields respond near would-be loops, stress energy often grows without bound. The growth then bends the geometry in a direction that removes the loop. This is not a decree against curiosity. It is a response from the same equations that correctly predict redshift, orbits, and waves. Thought experiments help by flushing out hidden assumptions. When someone says, "Go back and prevent," a quiet list of questions appears. What device maintains the path against perturbations? How is radiation handled? How are conservation laws respected at every step? Where do the fields that shape the corridor come from? And how are they confined? Without answers at that plane level, a paradox is a mirror reflecting imagination rather than an argument against known physics. The mirror is still useful. It shows where the edges are fuzzy and where sharp definitions would help. Data offer their own discipline. If signals from the future were possible and used in any regular way, archives would betray them. Statistical tests across weather records, markets, networks, and observatories look for correlations that arrive before their apparent causes. Long baselines exist in many fields. They show periodicities, drifts, and shocks that match local drivers. They do not show durable patterns of influence arriving early in ways that survive scrutiny. Individual coincidences are easy to find. A catalogue of robust anomalies is not. That absence is not proof that pastward travel is impossible everywhere. It is evidence that if it occurs, it does not operate in the wide domains we watch carefully. Quantum information brings a cautious kind of play. Circuits can be arranged so that, under post-selection, certain outputs are kept and others thrown away. The kept set can mimic some logics of closed curve behavior. No particles go backward. The trick rests on conditioning and computation. The exercise is not empty. It shows how consistency conditions shape outcomes in controlled systems and how probabilities can be adjusted under constraints. It also underlines the gap between logical mimicry and physical passage. An algorithm can imitate the bookkeeping of a loop without moving anything through it. Causality constraints show up in subtler ways. The no-signaling rules of quantum theory prevent faster-than-light messaging, even when entanglement correlates distant measurements. That barrier is tied to how statistics arise when outcomes are averaged over unknown settings. Models that promise to route a message backward must avoid stepping around this guardrail. Attempts that sneak information into boundary conditions or post-selection feed on the difference between calculation and intervention. Once an intervention is required, ordinary constraints return and the promise dims. Language can mislead if it reaches too far. Words like before and after carry a sense of a single universal sequence. Relativity refines that sense. Ordering is strict within each light cone and along each world line. Ordering across space-like separation is not unique. A paradox that depends on a universal now will disappear once frames are compared correctly and delays are included. Famous carriage and platform stories settle this easily. Less famous, more intricate systems can hide the same confusion unless the bookkeeping is done with honest coordinates and speeds. Paradoxes that evaporate under careful accounting are teachers. They correct the map without scolding the traveler. Entropy adds a quiet guide. The second law does not forbid rare fluctuations. It weighs them. Scenarios that require a precise sequence of improbable events to sustain a loop are being priced by that law. The cost grows rapidly with duration and size. A model may not violate any rule, yet still be physically irrelevant because the measure of worlds in which it operates is vanishing. In that sense, paradox resolution by unlikely coincidence is a formal option and a practical dismissal. The universe is large, but it does not often arrange a million coin tosses to land heads exactly when you need them. Human feelings meet these conclusions with relief rather than loss. The past remains a record, not a playground, and memory stays anchored. Regret keeps its gentle purpose to guide our next choices, without the burden of imagining repairs that physics will not allow. Wonder does not shrink. It shifts to questions that experiments can reach. How narrow are the windows that quantum inequalities leave? How does a full theory of gravity treat would-be chronology violations where semi-classical methods predict noise without bound? If those divergences soften, what new constraints take their place? Curiosity moves forward, not in spite of paradoxes, but because they point at gaps where honest work belongs. A small image can rest beside these facts without carrying them. Imagine a knot tied in a ribbon. Pulling on loose ends tightens the knot rather than freeing it. The harder the pull, the firmer the tangle becomes. Paradoxes are that knot. They tighten when tugged without plan. They loosen when the ribbon is turned the right way through geometry and experiment. The ribbon itself remains intact. The rules that make clocks agree, cones, fence influences, and energies balance stay in place while the knot is studied. Personal time does not tick identically for everyone, even when lives feel aligned. Differences appear in ordinary travel and altitude, small enough to miss, yet precise enough to measure. A person who spends many hours at cruising speed in the upper air collects a slightly different count of seconds than a friend who stays at ground level. The clock on the traveler's wrist shifts by a trace that instruments can recover, and the sign of that shift depends on the balance between motion and height. Higher altitude lightens gravity's pull and speeds the local rate. Greater speed slows it. Commercial routes thread both effects. Over many trips, the net amounts to tens of nanoseconds, a sliver that leaves birthdays unchanged but proves the rule. Orbit adds a broader canvas. Crews living months above the atmosphere circle Earth at high speed and modest height. Their onboard time advances by a few microseconds, fewer or more than ground time, depending on the orbit's exact parameters. Medical rhythms do not feel this difference. Daily routines, sleep cycles, and conversations follow their familiar cues. Yet, mission logs record the offsets, because navigation and rendezvous use them. When a capsule undocks and meets a station again after orbits apart, timing must be reconciled. The reconciliation is routine. It applies corrections that engineers can write on a whiteboard and that hardware can keep without complaint. Altitude alone influences personal time in a gentle, uniform way. Living at the top of a tall plateau places you a little farther from Earth's center than a friend at the shore. Gravity is slightly weaker, so the local second is slightly longer. Over a year, the difference remains far below any human sense. Precision clocks can hear it. Long comparisons between standards at different elevations resolve the shift cleanly, and papers report agreements within narrow bounds. Geodesy, the art of measuring height, has begun to use such clocks to map gravitational potential directly. In that practice, timekeeping turns into surveying. A deeper potential is a slower clock, and a slower clock is a lower point on a map. None of these differences rearrange ordinary affairs. Legal age is recorded by calendars, not by personal proper time. Employment records and school histories do not include relativistic adjustments. The tiny offsets matter only where systems care about microseconds or finer. Telecommunications that depend on synchronized frames between distant towers keep their schedules with internal corrections that include relativity implicitly. Power systems that require phase alignment across regions use time references disciplined by standards whose own readings honor the same equations. The network of services that supports daily life carries these facts silently, like a carefully tuned instrument that holds pitch while the audience listens without noticing the tuning itself. The lesson for people is straightforward. Time is shared, but not identical. Two friends can part, travel in different ways, and meet again with clocks that honestly disagree by a sliver. Neither device is wrong. Each has counted its own path through gravity and motion faithfully. The rules for comparing those paths are firm and simple enough to write down and use, which is why harmony is possible in complex systems that sprawl across continents. Harmony depends on agreeing about coordinates and signals, not on pretending that every second is the same everywhere. Health does not notice these differences because the scales are mismatched. Cellular cycles, hormonal rhythms, and restorative sleep follow patterns that tolerate far larger variations from stress, light, and habit. The body makes peace with noise and trains itself on cues it can sense. An extra microsecond gained or lost over days is invisible inside that flexible orchestra. That is why athletes trained at altitude adapt through blood chemistry rather than through clocks, and why recovery depends on nutrition and rest, not on relativistic bookkeeping. The physics is present, yet it is gentle enough to step back from the foreground of lived experience. Workflows in science and engineering feel the presence more directly. Timing arrays that correlate signals from distant antennas must account for path delays through atmosphere and hardware, Earth's rotation beneath the beams, and relativistic shifts for moving platform. Those tasks are routine rather than heroic. Software packages include the terms because the community has tested them for decades. When a new station joins a network at a high elevation, its equipment reads a reference that has already been adjusted to a common scale, so correlators can combine data without false offsets. The same quiet labor occurs in distributed sensing, where synchronized sampling across wide regions relies on time references that agree to better than a microsecond. Education often debates how early to introduce relativity into practical training. The answer, in practice, is early enough to avoid mistakes. Students who will work with signals, navigation, or precise control need to know that time depends on where and how fast, even if most days will not demand a fresh derivation. Knowing what to include in a model and what to ignore is a skill. Here, the guidance is clear. For consumer devices and local systems, classical timekeeping suffices. For global synchronization, high-precision survey, or spaceflight, relativistic terms belong in the model, and textbooks supply them. The smallness of personal effects invites a gentle perspective. Dilation is not a magical refuge from the passage of days. It is a correction that honest instruments can hear and that well-designed systems must include. The future can be reached fractionally sooner by traveling quickly or living high, but the gain is too slight to rescue lost time or to change a story. The value is understanding, not escape. That understanding anchors confidence in tools that guide airplanes to safe approaches, keep bridges monitored by sensors in phase, and allow distant laboratories to compare data without confusion about order. A modest image can rest here. Picture two finely crafted hourglasses made for different climates. The grains in one are cut to flow smoothly in dry air. The other is tuned for dampness. Each keeps perfect time in its proper room. Bring them together, and their rates differ slightly until you translate one reading to the other with a simple chart. Neither is wrong. Each is faithful to its environment. Human time is like that. It is faithful to path and place, and translation keeps friends and systems aligned. Seen this way, the human scale of dilation becomes comforting. The rules are sharp, but the consequences are kind. Small corrections deliver large coherence. The world remains navigable because the differences are predictable, and the prediction has been checked again and again. In that quiet, phones agree, schedules mesh, and travelers meet without worrying about whether their seconds are identical under the skin. The seconds need only be comparable with care, and care is something people can learn. A clock falling toward a non-rotating black hole keeps honest count along its own path. The outside story is different. Signals climbing from the falling clock arrive with longer intervals and lower energies. To a distant observer, the process seems to slow without end as the light stretches and the intervals widen. No one at a telescope watches the device cross the horizon in a finite external time. The traveler does not share that view. Proper time to the horizon is finite. The hands move, the mechanism ticks, and ground is reached in a span set by the starting radius and the mass ahead. Both accounts are correct because each uses its own ruler and clock. The geometry connects them without contradiction. Hovering is a sharper demand. Holding station just above a non-rotating horizon requires continuous acceleration provided by rockets or tension. As the radius shrinks toward the horizon, the required thrust grows without bound. No ordinary engine can supply that load, and any real vessel fails long before the edge. What breaks is not the rule of time. It is the capacity of matter to produce stress without yield, and to shed waste heat without limit. The physics that forbids hovering at the edge is the same physics that keeps bridges from standing without pillars and turbines, from running without exhaust. The horizon is not a wall to be pressed against. It is a place where static observers cannot exist. Rotation changes the neighborhood. A spinning black hole drags space-time around with it, twisting the local inertial frames. Within the ergosphere, a region outside the horizon, no object can remain at rest relative to distant stars. All timelike paths are pulled to rotate. This dragging permits an energy extraction process in which a carefully arranged split yields one fragment that falls with negative energy as measured at infinity, and another that escapes with more energy than the original. The bookkeeping is precise. Angular momentum is drawn from the whole, and the horizon area grows in a way that respects thermodynamic analogies. The timing of orbits near such a hole departs from circular ideals. Prograde paths nestle closer than retrograde ones, and the innermost stable circular orbit moves inward for aligned motion. Clocks on those orbits run slow relative to distant time by factors that depend on spin and radius. Signals from matter near these regions carry multiple time effects at once. Rapid motion shifts frequencies by relativistic Doppler factors. Gravity shifts them further as photons climb out. Path lengths around the hole modulate lags and echoes. The combination imprints variability on light curves and spectra. Interpreting that variability requires models that include time dilation, redshift, and frame dragging together. When models leave out any piece, the match to data degrades in ways that betray which effect was omitted. The story of time near these objects is a combined one, not a tale of any single term acting alone. Clocks carried by objects on plunging trajectories keep counting until tides demand attention. Tidal forces are gradients in gravity across the length of an object. Their severity depends on the hole's mass. For stellar mass holes, the gradients near the horizon are intense. A human-scale body would be stretched and compressed before crossing. For supermassive holes, the same gradients at the horizon can be gentle, and a compact probe could pass through without immediate rupture. The counting of seconds does not know this in advance. It records alike in both cases. The difference is in whether the mechanism survives to continue. The edge of a clock here is not a mathematical boundary. It is a material limit set by gradients and structure. Timing can also be traced by how gravity delays signals that skirt heavy masses. This Shapiro delay is a measurable increase in travel time for light passing near a massive object. In the environment of a black hole, the effect is strong. Radio pulses from a compact companion passing behind a heavy partner can arrive late by amounts that fit calculations using the exact geometry. The delay is a time signature of curvature. It says that even when paths remain outside the horizon, the clock in the signal feels the dip in the metric and notes it with a slow step. Combined with other terms, These delays allow reconstructions of orbits and tests of the metric's shape. Gravitational waves carry their own timing. A pair of compact objects spirals inward as they radiate energy. The waveforms phase, tracks, orbital frequency, and separation. Near merger, the phase accelerates in a way that encodes strong field time dilation and redshift. Observatories that sense these waves match templates computed from relativity to the measured strain. The match depends on getting time right as gravity intensifies. Templates built without proper redshift and frame dragging would slide out of sync with observed chirps. The success of matched filtering is a clock reading of the field itself during the most violent moments. Thermodynamic analogies add another layer. Horizons behave as if they carry temperatures and entropies, with surface gravity playing the role of temperature and area standing for entropy. Those identifications are not mere metaphors. They arise from combining quantum field theory with curved backgrounds and lead to predictions like thermal emission from horizons. The time relevant here is set by surface gravity and by how fields respond to the boundary. It is not a personal clock, but a scale in the spectrum of fluctuations near the edge. The association strengthens the sense that time near a horizon is rich with structure, anchoring both kinematics and statistical behavior. No ordinary arrangement pauses or reverses time near these objects. Hovering at the edge cannot be sustained. Dragging time backward is not available through any allowed motion. What remains are honest, dramatic slowings and shifts that instruments can trace. Those effects are not loopholes. They are the geometry written plainly. Movies that portray years passing for distant scenes, while hours pass near a hole, rest on the same relation, scaled for drama. The scaling can be extreme, near deep curvature, but it always respects causal order. Signals still climb. Outward at light speed locally, and cones still fence influences. The marvel is large without breaking sequence. A modest image can sit beside these facts. Think of a deep valley where sound moves true, yet echoes lengthen and voices drop in pitch as they climb to the rim. The singer on the floor keeps time with a metronome in their hand. The listener on the ridge hears phrases stretch and tones fall. Neither is wrong. Each hears what the path and the air demand. The valley does not erase beats, it reshapes their travel. A black hole does the same for seconds, delays, and colors. The edge of clocks is the edge of survivable gradient, not a magical hinge. These conclusions leave wonder intact. Time near compact gravity is malleable, structured, and measurable. It is not reversible by craft or comfort. The rules that keep sequences ordered survive in the very scenes that stretch them most. That endurance is a kind of tenderness in the laws, allowing astonishment without surrendering coherence. It is enough to lull the mind even as the facts remain crisp, and enough to close the eyes with a picture that does not contradict the instruments waiting for morning. The warp idea begins with geometry, not engines. A metric can be written in which a compact cabin sits in free fall, while space behind it stretches and space ahead compresses relative to distant coordinates. The cabin moves faster than light. Inside, nothing breaks the local limit. The craft feels no thrust because its world line is geodesic within the bubble. This construction is precise mathematics in general relativity. Coordinates can slide in ways that let distant landmarks pass more quickly than light would cross them, even though every local measurement honors the same ceiling. The cost appears in the source terms. To curve space that way, the stress energy must contain negative energy density and unusual pressures arranged with tight tolerances in a ring or shell around the cabin. Classical matter does, and not offer those signs. The energy conditions that ordinary fields obey exclude them over extended regions. Quantum fields allow small, short deficits. but inequalities restrict their size and duration. The ledger does not balance at human scales. Later sketches massage the shapes. By changing how the bubble's rim thickens, by tapering profiles, or by trading radial for azimuthal stress, the total negative requirement drops in calculations. The signs, however, remain exotic. The deficit still must exist, and the bounds from quantum theory still limit accumulation. The bubble also carries horizons at its front and back edges when it moves superluminally in coordinates. Those horizons split inside from outside. A signal from the cabin cannot reach the front edge to steer the bubble's leading face. A signal from outside cannot warn passengers of obstacles or targets in time to adjust. Control becomes non-local in a way that physical devices cannot achieve. Even at subluminal coordinate speeds, horizons linger in limiting cases, and the communication problem persists in softened form. A design that cannot be steered from where its occupants are is already a cautionary tale. Fields near the rim bring another concern. Quantum fluctuations respond to strong gradients in geometry. Calculations show that the stress energy of quantum fields can pile up at the bubble boundary. In some analyses, the energy density seen by observers near the edge grows large as parameters tighten, implying radiation baths that would threaten passengers if the configuration were turned on or adjusted abruptly. The same back reaction that hindered time loops appears here as heat and instability. One can smear the gradients to calm the response, but that spreads requirements and deepens the inventory problem. A quiet rim asks for more of the same rare commodity. The design moves between scarcity and noise. Navigation is not a detail. A coordinate region with front and rear horizons separates the cabin from the very world it intends to traverse. One workaround proposes external beacons that shape the bubble from a distance, like tugs pushing an invisible hull. That approach replaces one difficulty with another. The system must arrange and maintain negative energy and precise stresses around a moving target whose communication is limited by its own horizons. The coordinating beacons themselves must know the environment ahead and act coherently in a field they cannot fully probe. The control loop is fragile in theory and seems untenable in practice. Free fall inside the cabin is no comfort when the helm cannot see the sea. No laboratory has created a warp-like metric in general relativity coupled to known fields, even at microscopic scales. Analog experiments in media mimic kinematic features, effective horizons for sound or light, yet they do not source space-time curvature. They teach about waves, not travel. Metamaterials guide electromagnetic fields with tailored refractive indices. They demonstrate that perceived paths can bend through media without requiring gravity. Those devices are useful for cloaking and beam shaping. They do not move geodesics for matter or change causal structure. A warp metric remains a gravitational construction, not an optical trick, and gravity answers to stress energy with signs that real materials have not supplied. The thought experiment still earns respect. It shows that faster than light can mean faster than light relative to distant coordinates, without asking any occupant to outrun a local photon. It shows that general relativity is flexible enough to accommodate astonishing coordinate behaviors while protecting local laws. It also marks where nature has placed strong locks. Energy condition violations of the needed size have not been observed. Quantum inequalities prevent building a warehouse of negative energy by stacking small deficits. Horizon structure complicates control. Radiative back reaction punishes sharp rims. Each issue alone is heavy. Together they outline a boundary. If a brief image helps, picture a treadmill imagined beneath your feet that carries the ground away while you stand composed. The sketch is clean. You do not run. The belt moves the world. For the device that matters, the ground itself, one must find fibers that push harder than empty space and pull softer than nothing. The concept clarifies what moving without moving entails. The inventory reveals that the fibers do not exist to weave the belt. Between concept and inventory lies the gap that separates principle from practice. The lesson is calm rather than crushing. Coordinate speeds can overtake light, while locals remain law-abiding. The geometry allows it, but geometry is not free. It is paid for by sources. Where those sources contradict durable observations about fields, or where quantum theory caps their useful magnitude and time, the road ends for real machines. That end is not a verdict on curiosity. It is the present map. A future theory could rearrange the catalogue of allowed stress energy, or reveal new effective fields with different bounds, or show ways that semi-classical estimates fail near microstructured vacua. Until then, warp metrics teach more about the structure of general relativity than about routes to other stars. They are mirrors that reflect the theory's grace and the world's restraint together, leaving the mind quiet and the night untroubled. A white hole is a time-reversed partner of a black hole in the equations. Where a black hole admits no escape through its boundary, a white hole admits no entry. Matter and light flow outward across its surface, never inward. In maximally extended, idealized solutions, these regions appear naturally alongside black holes in a symmetric diagram. They complete a picture, the way a mirrored page completes a pattern. The symmetry is exact in the mathematics. The question is whether nature prints both pages. Observations offer no admissions for white holes so far. Catalogues of bursts and flares across the sky, gamma-ray flashes, fast radio spikes, superluminous supernovae fit models involving mergers, collapse, magnetar storms, and accretion behavior. Those models predict multi-wavelength signatures and host environments that match datasets collected for decades. Persistent, boundary-only emission from a white hole does not match these families. The sky is busy, but its engines resemble familiar compact objects, not one-way fountains. The narrative pull remains strong. Enter a region that forbids exit. Emerge from a region that forbids entry. The asymmetry suggests a shortcut toward later external times. The traveler's proper time could be short if the passage connected interior to exterior directly, while distant clocks accumulate longer intervals outside. The trouble is in the hinge, a traversable connection. Classical general relativity closes that corridor. The simple bridges connecting black and white holes in vacuum pinch off before anything crosses. Stable, open routes require exotic support, negative energy, special stresses, or global structures that real cosmology does not share. Quantum gravity is invoked as a possible craftsman for such hinges, yet concrete, testable mechanisms have not been established. Speculation links certain transients to white hole burps, but competing explanations rooted in known physics fit the statistics and the spectral details more naturally. Even if some quantum process briefly manifested a white hole-like phase in a collapsing object's life, coupling that phase to a specific traveler's path would ask for control where no handles exist. Tidal fields near collapse are strong. Radiation environments are hot and chaotic. The geometry evolves rapidly. A person-sized vehicle does not carry dials that tune an evaporating quantum structure toward a desired outside date and destination. The coupling between microstates and macroscopic guidance is exactly what no current theory supplies. Without it, the picture remains a clean drawing. The arrows point outward. The labels say, "No entry." The page is interesting because it balances a book, not because it opens a door. Theoretical work does draw insight from the white side. Time reversal clarifies what energy conditions and horizons demand. It anchors proofs about areas and thermodynamic analogies for black holes, where surface gravity plays a role like temperature and area plays a role like entropy. In those arguments, white holes behave like boundary cases and help show why certain processes are one way. They add structure to the space of solutions and give context to the irreversible character of collapse. That service does not translate into sightings. It refines understanding of black holes rather than creating new characters for the sky. Searches continue in good faith. When an unexplained transient arrives, teams test template banks that include many possibilities: rates, environments, polarizations, and counterparts in other bands help narrow options. The burden of proof for a white hole interpretation is properly high because other engines can mimic bursts with similar energies and timescales. So far, distributed archives of high-energy events show variety without requiring the time-reversed object. The absence remains a reported result, and it carries weight precisely because the sky has been generous in other surprises. Jets, mergers, repeating radio sources, tidal disruption flares. When a new class is required, evidence usually arrives in multiples with consistent traits across instruments. White holes do not yet live in such a family. For time travel stories, the white hole serves as a clean metaphor. It is a source without a past, a stage door that opens only outward. The metaphor tempts a leap. If one could aim for that door from a black hole's interior, one might emerge elsewhere and else when. The temptation ends at the same place as wormhole tales. The supporting geometry requires matter unlike any we have seen, and stability demands that quantum fields behave in ways calculations often deny. The safest positioning for the metaphor is not as a tool but as a mirror. It helps reveal the asymmetry of processes we can test. Collapse builds horizons that trap. Expansion reveals boundaries that expel. The two complete a diagram that teaches while the observable universe keeps one page active and leaves the other as a gloss. If a restful image fits, imagine a gate painted on a wall opposite a real doorway. The painting follows the doorway's lines precisely, reversed as if reflected. It balances the room, explains the layout, and pleases the eye. No hinges sit behind it. Press your hand to the surface, and you meet stone. The real door remains useful. The painted door remains instructive. Between them, the room makes sense. That is the role white holes play at present. Symmetry that organizes knowledge, not an entrance for travelers. The night can keep that picture without stirring, and the facts rest easily in its frame. Quantum theory often speaks with grammar that seems to loosen time. A line in a diagram runs backward and is reinterpreted forward as an antiparticle. A wave function spreads into regions that a classical point would never touch and assigns weight to passing through a barrier. Two detectors click in ways that share correlations over long distances without a signal passing between them at the moment of choice. Each of these is real. Each has been tested in many guises. None opens a pathway for people or messages to earlier days. The backward arrow on a diagram is a compact bookkeeping rule that preserves causality in the sums that create measured probabilities. The tunnel is an amplitude that reshapes distributions here and now. It does not carry a controlled bit upstream in time. The correlation from entanglement appears only in joint statistics and refuses to become a wire for faster-than-light communication, because marginal distributions at each station remain random until results are compared within ordinary light cones. Delayed choice experiments underline that refusals are deep, not technical. When a measurement basis is decided after a particle seems to have committed to a path, outcomes still follow rules that prevent signaling. The choices alter correlations, not the arrival of a usable message. Leggett Garg tests probe whether macroscopic realism properties existing with definite values, independent of observation, can survive alongside quantum predictions. Violations appear in carefully shielded systems. They indicate that classical pictures fail in the regimes tested. They do not furnish macroscopic devices that change the order of events in recorded histories. Decoherence grows rapidly with scale. Interactions with environments entangle states with countless degrees of freedom and suppress interference terms. The nicely drawn quantum behaviors that intrigue at small scales give way to classical outcomes that carry no time-bending privilege when many particles and finite temperatures join the scene. Quantum technologies flourish within these boundaries. Clocks that use narrow optical transitions measure time with extraordinary precision. Sensors based on atom interferometry read tiny accelerations and potentials by tracking phase. Communication protocols exploit entanglement to detect eavesdropping and to distribute keys with security guaranteed by physics. None of these tools allows a message to be arranged in the past. They improve what can be known about the present and near future by reducing noise and sharpening comparisons. The benefit is clarity, not a tunnel under causality. The same formal structure that enables sensitivity, unitary evolution, punctuated by measurement, also guards the order of influence. Where quantum theory touches gravity, mysteries remain. Singularities in classical solutions likely mark the limits of the description rather than physical infinities. The early universe's smoothness and fluctuations come from quantum seeds that a more complete theory should model directly. Information seemingly lost to horizons pushes theorists toward resolutions that preserve unitarity while respecting locality as far as possible. Proposals range from subtle correlations in outgoing radiation to modified near-horizon structures that remain consistent with observed black hole shadows and spectra. These frontiers are serious because they tie the pillars of modern physics together. None, in tested forms, offers an invitation to change chronology. Where tensions appear, they usually ask how information is encoded and recovered, not how an influence leaks backward to an earlier surface. The discipline that has held in all combined tests no superluminal signals, no usable retrocausal channels, continues to guide acceptable ideas. Language sometimes misleads by leaning on imagery that outpaces what equations allow. Saying that a particle borrows energy in a virtual excursion is a way to summarize integrals, not a license for debt that matures into macroscopic violation. Saying that a wave function explores all paths invites a picture of purposeful scouting that the mathematics does not require. The integrals sum contributions and weight them by phase. No agent decides. Clarity returns when statements are translated back into operational predictions. What prepares a system, what interactions occur, what detectors read, and how records correlate. In those terms, the story becomes crisp, and the temptation to find a bridge fades because no bridge appears in the numbers that compare to instruments. If a brief image can sit quietly here, think of ripples on a pond meeting a thin strip of reeds. A portion of the pattern slips through the gaps and reappears beyond the reeds, shaped by spacing and depth. The interference is real and calculable. The ripple has not sent a message to its earlier circles. It has followed the structure before it, altering what appears farther along. Quantum tunneling and interference work like that in the parts we can test. They redraw patterns ahead. They do not return to the first stone and change where it fell. The cleanest statement is calm. Quantum theory is subtle and powerful. It surprises routinely. In every combined test with relativity, it has kept causality intact in measured outcomes. Correlations that defy classical expectation remain bounded by no signaling rules. Amplitudes that allow passage through barriers remain probabilities that reshape present distributions. Reinterpretations of lines in diagrams help sums behave, not history's reverse. The strangeness is generous without becoming a key to yesterday. That balance gives both wonder and rest. Extraordinary claims earn attention by meeting ordinary standards with unusual success. For a claim about time travel, the bridge from story to acceptance would begin with records that refuse simpler accounts. Those records would need timestamps that survive cross-checks in independent archives. A change attributed to influence from the future would appear identically in systems maintained by unrelated groups, observatories, financial feeds, seismic logs, public network time services, and would do so in ways that match the constraints of relativity and no signaling. If a message were claimed, it would have to arrive with a structure that defeats forgery tests, drift analyses, and corruption audits. If an object were claimed, its provenance chain would need to pass materials science, isotope ratios, and microscopic wear studies designed to catch fabrication. The standard is not antagonistic. It is the same path by which new physics has always entered. An anomaly survives simple explanations, then repeats, then proves predictive, then yields to a mechanism that integrates with existing laws or replaces them smoothly. Archives already serve as quiet sentinels. Astronomical surveys hold nightly images and spectra that date back decades, with checksums and version histories. Timing networks log offsets and drifts, buoy standards. Seismic stations record tremors continuously with independent power and storage. Market feeds and exchange records keep microsecond resolved trades. If interventions from the future were frequent or accessible, statistical patterns might emerge across such collections. Anomalies could show correlations that do not fit known couplings, or prefigurations that match later events more tightly than chance allows across many trials. Searches for such patterns return the same answer. Fluctuations behave within expected distributions. Once known confounders are included, and surprises that rise above thresholds find local causes on investigation. The data are not silent because no one listens. They are well listened to and speak steadily. A persuasive case would also include negations. If a purported traveler brings knowledge of specific, verifiable events, checks can be designed to separate coincidence from causal intelligence. Predictions would need to be timely, detailed, and repeated, without access to privileged sources, and they would need to survive conditionalization that removes hindsight bias. If a device claims to send signals backward across short intervals, carefully isolated labs can mount trials that randomize targets and lock protocols before runs. Results that exceed preset statistical thresholds can be probed for leakage and artifact. The bar is high because error patterns masquerade as miracles easily when controls are weak. Laboratories have trained themselves on those lessons because physics has earned its successes by defeating its own wishes in controlled light. The absence of credible, consistent anomalies across deep baselines does not prove impossibility. It sets a practical prior. It also sets a direction for curiosity. Concentrate on regimes where theory suggests deviations might be largest, or where new detectors open windows. That strategy paid for superconductivity, which revealed itself through resistance dropping in metals at low temperatures, for the cosmic microwave background, which painted a thermal glow across the sky, and for gravitational waves, which chirped in instruments after decades of patient improvements. In each case, the claim grew by explaining stubborn data in a way nothing else could. Then by repeating under independent control, time travel into the past would be at least as public in its footprints. It would not hide well once it touched instruments that run without pause. Standards extend to presentation. Results should be pre-registered where appropriate. data shared openly with redactions only for privacy or security, and analyses reproduced by groups with no incentive to agree. Journals and archives should record versions so that later reinterpretations can be traced. Claims that bypass this path in favor of authority, secrecy, or fragile narratives of provenance do not meet the bar, not because gatekeepers are cruel, but because the world has learned patiently, sometimes painfully, that agreement among strangers is the only shield against self-deception that scales. If someone arrives with a story about yesterday, the fastest way for that story to earn comfort is to submit to this slow machinery and pass. Relativity itself supplies constraints that any evidence must respect. No signaling theorems prevent faster-than-light messaging in quantum protocols. Any claimed backward signal would need to navigate that without sneaking in a selection bias that only looks like retrocausality. World-line comparisons require careful accounting of frames, delays, and local time. Many paradoxes evaporate under this bookkeeping, revealing that supposed contradictions arose from implicit assumptions about a universal present. Solid claims would show awareness of these subtleties from the outset and would present analyses that reflect them, the way astronomers routinely translate observatory times to a common coordinate scale before comparing light curves. If a gentle image can rest at the end, picture a well-lit hallway with doors along its length. Some doors already open and lead to rooms where instruments hum and notes are taken. Other doors are new, added when fresh ideas survived trials and earned a place. The door for time travel into the past is not locked in anger. It stands without a knob because no one has presented a key that fits the building's standards. The hallway remains bright, tools are ready. When a key arrives that turns easily and opens onto a room with repeatable, shareable work, people will walk through together. Until then, the sensible stance is to keep the corridor tidy and the lights on. This stance suits a sleepy mind. It is not a rejection of wonder. It is a way to let wonder rest against evidence without strain. The world has room for surprise. It also has a method for testing surprise. Between those two, the night stays gentle, and the story can pause without confusion. Time travel, as a phrase, promises leap. Physics, as a practice, delivers steps small, reliable, quietly breathtaking. Those steps are real. Clocks slow with speed, seconds stretch under gravity, and the world fits these truths so well that our satellites and systems depend on them. The leaps we imagine belong to the edges, the equations that tease tunnels and loops if matter ever dares to act beyond the ordinary. Yet every time we test them, the universe answers with calm order. Cause stays ahead of effect. The story remains stable, patient, kind. That balance isn't a letdown, it's mercy. It means we live in a cosmos that keeps its promises. Every second you spend, every heartbeat you feel, is measured honestly in your frame of the universe. Your time has value because it's yours. As you rest tonight, don't wish to escape time, shape it. Protect the minutes that make you better. Stretch them toward learning, toward stillness, toward someone who matters. The future is already forming quietly, in your habits, your patience, your if. If you felt lighter tonight, like, subscribe, and share. It helps this slow science continue, returns new episodes to you automatically, and gives someone else a softer way to sleep. When your thoughts begin to float, let them. The universe is still counting faithfully for you. Good night.